Hi guys, I'm Olivia and I am in the laser lab today with Wendy. Wendy, do you want to tell us about yourself and your research?
Yeah, hi. So I'm a final year student studying both mechanical and biomedical engineering. My thesis topic is on CFD simulation of patient-specific carotid artery stenosis. And it's a very interesting topic because the geometries that I use are real patient cases. And the results can provide meaningful information, so it can help surgeons to determine whether the patient requires surgical treatment.
Yeah. So you mentioned patient-specific geometry. Did you get that geometry from the surgeon? Or?
Yeah, so I got 15 patient geometries from the surgeon.
So the geometry was from the surgeon?
Yeah.
And you mentioned you run CFD analysis.
Yeah.
Do you want to tell us about what's your methodology and how do you do that?
Yeah, so I use ANSYS Fluent for my simulation.
Yep.
And so I have 15 patient geometries. And the boundary conditions I use are also patient-specific velocity profile.
Yep.
So I started from steady state analysis and moved to transient simulation.
Yep.
Yeah.
So you ran transient simulation.
Yeah.
So how did you get the velocity profile and why is it so important to run a transient analysis?
So for transient analysis, I can get different hemodynamic factors, including velocity profiles, time average wall shear stress, and oscillatory shear index. And because these parameters can predict some issues within the carotid arteries. So for example, if the wall shear stress is too high, then it may damage the endothelial cells. And if the wall shear stress is low with high oscillatory shear index, then it means that there could be possibilities of plaques to build up.
Yep. So essentially, the CFD analysis helps you to see different factors, different parameters that you can help to understand what the vessel is trying to react on that. So were there any important parameters that you look at besides the wall shear stress? Did you look at velocity and
velocity and oscillatory shear index.
Yeah. So did you manage to see any correlation on that?
So for the areas with low wall shear stress, they usually have high oscillatory shear index. And the velocity profiles are kind of the low velocity recirculating turbulent flows.
So the velocity helps you to see whether it's turbulent flow and recirculation soon. Okay, that's pretty cool. So I guess as an undergraduate, were there any challenges, because it's such a big topic that you are looking at geometry and real patient geometry and stuff like that. Were there any challenges along the way when you do your analysis?
So some of the challenges include time limitation because I ran all the cases under one cardiac cycle. But for more accurate results, I should probably run them under 3 cardiac cycles. And another limitation is mesh because my license have a restriction of I can't have over 500,000 mesh elements, so that was another limitation for me.
Okay, so I guess how did you overcome the different challenges that you had?
So I actually ran one case under 3 cardiac cycles, and I compared the results of one cardiac cycle, and fortunately there weren't too many differences within the results.
So you compared your different analyses and then run a model. That's pretty cool. So how do you think that your research can further develop from here?
So for my thesis, I made a few assumptions. I assumed the flow is Newtonian and the vessel walls are rigid, but in reality they are not. So blood isn't always Newtonian and there is wall elasticity. So I would say these are the areas that should be taken into account for further analysis.
Okay, cool. I hope that the results that you get will be able to help surgeons in the future. Thanks for chatting with me today.
Thank you for your time.